Good. Well, today we come to the last topic for the course, which is generative adversarial networks. So that'll take up about the first hour or so, and then after that we'll just have a bit of a review of all the topics in the course. So I'm trying to put this in a bit of a context. So I'll talk about artist-critic coevolution, some older work on coevolution paradigms and interactive evolution and so on, and then this is sort of background, and then the main topic, which is generative adversarial networks. So there's this general paradigm of artist-critic coevolution. So this is where you have two modules in the system. You have an artist and a critic, and the artist is you have a set of real images, and the artist is trying to generate images which in some way resemble the real images, and the critic is trying to tell the difference between the real images and the ones generated by the artist. So the critic is rewarded for its ability to distinguish the real images from the ones generated by the artist, and the artist is rewarded for fooling the critic into thinking that the images it generates are real. So you get this kind of tension. It's like a game between the artist and the critic that they're playing against each other. And you get different results depending on what you choose to play the role of the artist and the critic. So the earliest work in this area was a human would play the role of the critic, and then later on these kind of a self-organizing map or a two-layer neural network, and then more recently a convolutional network. So the very first work in this area goes back to 1986, a book by Richard Dawkins called The Blind Watchmaker, and he was trying to explain to a lay audience how evolution works, so he developed this little kind of interactive software, and where these images evolve with some sort of genetic program, and 15 images would appear on the screen, and the user that are slightly different to each other, and the user is invited to select one or more images that they like, and then you press the button and the system goes away and generates another set of 15 images which are kind of slight modifications of the ones that were selected. And the idea is that over time you may get something that's more and more to your liking. Now, of course, it's 1986, so it's extremely primitive kind of Apple Macintosh graphics, and the generation was something called biomorphs or L systems, and so it's all a bit kind of hokey by today's standards, but with enough effort and a bit of imagination you can get an image that looks like a scorpion or a Spitfire or a lamp or various other things. Okay? Now we fast forward to 1991, and we see work by Carl Sims along the same lines, but with more fancy computation. And here, so again, it's this kind of interactive evolution where you have to select from 15 images. And here the artist is, I won't go into the details, but it's evolutionary computation. The artist is a genetic program, and it's used as a function to compute red, green, and blue intensities for each pixel location. And this is an example of an image that might be generated. So let's say x is minus 1 here and x is plus 1 here, and y is maybe minus 1 here and plus 1 here. So every pixel has a certain x and y value. You feed that into this little genetic program and it spits out three numbers for the red, green and blue intensities. And go forward to 2011, again, the same underlying paradigm, but this time what's called a compositional pattern producing network, a CPPN, which has the capacity to produce slightly more vivid or slightly more realistic images, not quite realistic, but in comparison. So there's a website where you can, called pickbreeder.org, where you can go and sort of play this game yourself. You know, you can click on some evolution, you can start with an existing image and go through this process. And if you've got the patience to go through maybe 50 or 60 generations, you may get to an image that looks like a planet or a racing car or an apple or something like that. Yeah, but it's kind of a long process. So this requires a fair bit of human effort. So then the natural question arises, well, can we sort of cut the human out of the equation and replace the critic with an automatic process? And so the first kind of early work in this direction was in computational aesthetics by Mercado et al. In 2008. So they generated a genetic program as before, very similar, but instead of a human, they've got a little small neural network, but the critic is very primitive. It's just one of these it's not a convolutional network, it's just one of these old-fashioned neural networks that takes a small number of inputs and has two layers. So the way it works is you take the image and you plug it into OpenCV and you compute a bunch of statistical features of the image. You compute the entropy of the color spectrum, you compute the size of the second, the largest and the second largest contiguous blob in the image and certain other things like this. You get out about maybe 17 numbers and then you feed them into this little neural network. And the neural network on that basis alone is trying to classify whether the image is real or fake. So it's fairly primitive, and as a result you get images which are kind of not very realistic. Okay, well, that's kind of the background. Now then, but you'll notice this is very similar in intent to what we were discussing last week with these autoencoders, because what we want to do is to be able to generate images. And if you remember, we looked in particular at this variational autoencoder. This autoencoder, we have the input and then we have the hidden units, which gives us certain latent features, and then we have the output. But we want to make sure that we want to make sure that the hidden features, that when those original images are mapped into these hidden features, they kind of spread out to approximate a Gaussian distribution, so that then if we pick a random point from the Gaussian distribution, we expect to get a realistic looking image. And so the way this was done with the VAE was you had an extra term in the loss function. You had one loss term that was the reconstruction loss between the input and the output, and the other term was the KL divergence between the standard normal distribution and the one specified by the network. So because of this loss with the KL divergence encourages these things to spread out and fill a whole space. And we saw that this actually produces pretty good results, at least in terms of these digits. But then when we move on to faces, they often get a sort of blurry result. Yeah, you can recognise them as faces, but there's a bit of sort of blurriness there. So, Ian Goodfellow, who's the main author of our textbook, and he was working in Montreal in Joshua Bengio's lab, so he and some collaborators got together and said, well, you know, maybe how can we fix this to make the thing produce more realistic looking images? Well, we can bring in this paradigm of artist-critic coevolution. We can train another neural network to be given these images, and that neural network will try to tell the difference between these images and real images. So it's a very clever idea because if the network is, the discriminator network is going to be trained to focus its attention on whatever's most unrealistic about these images, and then the generator will be forced to correct those problems. Okay, so this is where we get to the concept of generative adversarial networks. So you see it's quite similar to, it's basically the same as the artist-critic coevolution, but here we use sort of different terminology and different notation. So we use X to indicate the real images, and then we have this generator. So if you remember, with the autoencoders, we had an encoder and then we had a decoder. So here, this is the same as the decoder, but we call it the generator. So we use G for the generator. So the generator is given a set of random numbers. You have to specify the dimension. Okay, so it's going to produce an image. That X tilde is going to be an image. And so in other words, it's specifying red, green, and blue intensities for each pixel. This Z is maybe you have, say, 256 variables, and you know, so you have Z1, Z2, Z3 up to Z256, and each of those variables is going to be chosen randomly from a Gaussian distribution. So these Zs here are called latent variables because they're intended to capture some abstract features in the image, and then the generator has the job of taking those, those latent features and turning them into an image. And before I get to the equations, let me just show you some examples of output that you get from this process. This is kind of old work now. This is from 2015. But you kind of get the idea. This is a GAN that's been trained on images of bedrooms. You know, bedrooms mostly in hotels and in people's homes. And then it's been asked to, after it's been trained, then you try to use it to generate fake images of bedrooms. So these are not, every one of these is not a real bedroom. It's actually a fake bedroom that's been generated by this GAN. And you can see they look very realistic. Now, if you look closely, you might see little anomalies, like you might see a sort of Siamese bed or something. You know, I'm trying to. This looks like these two beds are somehow joined together. It's not. There's two bed heads, but only one bed or something. And this bed doesn't look quite the right shape. It's sort of bent around a bit. So you do get sort of slight anomalies when you look at the small details. But in general terms, they do look very realistic, much more realistic than what you get out of other methods like this. Okay. So this is how it works. You have a generator and a discriminator, and each of them, we just for the purposes of notation, we use different variables for the weights in the neural network. So we use theta for the weights in the generator, and we use phi for the weights in the discriminator. So the generator generates an image x from specified latent variable z that are chosen from a standard normal distribution, and the discriminator takes the image and produces a number between 0 and 1, and the idea is that it should assign a high number to the real images and a low number to the fake images. Okay? So these generator and discriminator play a two-player zero-sum game, and this is what they try to compute. Now I'm just going to where are we? I'm just going to go into a few slides from this is from an invited talk that I gave last year at the ACCV conference. There's just a couple of extra slides in here that maybe illustrate this a little bit better, but essentially have the same content. So this is the equation here. So this is it looks quite busy, but let's just unpack this a little bit at one piece at a time. So d psi of x, this x is the real image, and d of x is the score that the discriminator assigns to x, and so we want that to be close to 1. So log of that, so that E is the expected value over the set of real images x of this value log of d psi x. Now log of 1 is 0, but log of a number smaller than 1, d psi x has to be between 0 and 1. It's got from like a sigmoid. So if the output is 1, then log of that is 0, and if it's less than 1, then the log will be negative. And so the discriminator is trying to maximize this. You know, if it's the number's always 0, the number's always negative, but it's trying to get it up as close to 0 as possible. So that's why we have max over psi. The discriminator is trying to maximize that number. Now, on the other hand, the discriminator is also for the fake, so these are the fake images here. So to get a fake image, you start with a random variable z. So this is the expectation over randomly chosen z's. And you feed it into the generator, and you get a fake image, and then you feed that fake image into the discriminator. And so you want this to be a value close to 0. Now, in the very first original version of the GAN, this was the equation. So instead of trying to maximize log of the thing, you try to maximize log of 1 minus that. Yeah. So again, like you want this to be close to 0. So if it was equal to 0, then 1 minus that would be equal to 1, and so the log would be 0. And so again, it makes sense for the discriminator to maximize this. So the discriminator is being trained by backpropagation, and is trying to maximize the sum of these two terms, because it's just from its point of view, it's just a classification task, right? Real and fake images. Now, what about the generator? Well, the generator doesn't have, the generator can't do anything about this term. This term is just about the real images, but the generator can do something about this. It can the generator is trying to fool the discriminator, so the generator wants the discriminator to assign a number close to 1 for the fake image, and so the generator is trying to minimize this expression. So this is, in this original formulation, it becomes what's called a zero-sum game, because there's this expression and the discriminator is trying to maximize it and the generator is trying to minimize it. Okay. Now, but what's interesting about this approach is that you're actually back propagating from the you're back propagating from the you're back propagating through the discriminator and then through the image and then into the, sorry, I'll show you the architecture in a minute, but you got the latent variables going into here, and this is the image and then the discriminator. So when you back propagate, when you're training the generator, you're back propagating from here through the discriminator and then back through the image into the generator. So you're treating the image as if it were a layer in a sort of combined network somehow, and you're back propagating actually through here into the generator, which is something that hadn't kind of been done before. Okay, now it turns out that, so this is the original formulation. Now it turns out that actually this expression doesn't give terribly good results, and the reason is that it puts too much emphasis on images that are correctly classified. If you sort of look into the details of this, that expression there, if you've got, let me think about this for a second. Yeah, maximizing the generator, right? So let's say the generator is producing images, and it wants the discriminator to assign a high value to those images. So you think about this. Let's suppose you produce one image which is good, which the discriminator is giving 0.8, and another image which is poor, and the discriminator is only giving 0.1, right? Now, should you put your effort into taking the good image and making it even better, lifting the 0.8 to the 0.9, or should you instead, if you've got a choice, would it be better to put your effort into taking the very poor image that got the 0.1 and lifting it up to 0.2? That's really the issue at stake here. So the original model would put its emphasis on taking an image that's already good and making it even better, but at the expense of leaving the bad images as they are. If we replace, instead of minimizing log of 1 minus d, we maximize log of d, then we do the opposite, which is we put more emphasis on taking the really bad images and trying to improve them, which is better, right? So it's actually better to do it this way rather than this way, and it's like there's a lot of sort of weird terminology around this, because it's often claimed that a GAN is a zero-sum game, but actually when you do this, it's no longer a zero-sum game. But it's more logical this way. And there's another variant called the Wasserstein GAN, where you replace this with another slightly different function, but we won't go into all those details.
How do you train the discriminator? Is there any varying features?
Good question. Right, so the discriminator is still trying to maximize the top expression. So this change is only in how the generator is trained. Yeah, good question. Okay, so this is, and if you compare this to those earlier kind of evolutionary approaches, with the evolutionary approach, normally the evolution just sort of produced one image at a time, whereas this GAN approach, one network will produce many images. Once the network is trained, it may take a long time to train, but once it's trained, I can feed in a large number of random Zs, and it should produce a new image for every Z. So it's a very powerful technique. As I mentioned, the differentials are backpropagated through the discriminator into the generator, and the images that are produced are much more realistic than in previous approaches. Okay, now here's some details. I think these details help to understand what's going on. So this is how it's done. We split it into two kind of phases of training, or at each epoch we do two stages of training, one for the discriminator, one for the generator. So first we train the discriminator. We sample a mini batch of latent samples, Z1 to Zm, and we also sample a mini batch of real images, X1 to Xm, and then we train the discriminator by gradient ascent on psi because we're trying to maximize this. And so with the generator, remember the discriminator is doing a classification task, so the same as any classification task, it's helpful if we balance out the two classes. So we're giving it the same number of, making use of the parallelism on the GPU. We're giving it the same number of positive and negative examples. We're giving it M real images and M randomly generated fake images. Right? So that's the discriminator. Then we move on to the generator. Now, theoretically, we could train the generator on the same samples that we chose for the discriminator. We chose samples Z1 up to Zm, and we used those to train the discriminator. We could just take exactly the same samples and then use them to train the generator. That gives a reasonable result, but it turns out that you get a slightly better result if you sample a fresh batch of latent variables and then train the generator on that. It's just because there's a bit more diversity kind of thing. So you sample MZs from the normal distribution, and you feed them through the generator and the discriminator, and then you train so you're using the discriminator here, but you're not changing in this second stage. We need to use the discriminator to backpropagate the differentials into the generator, but we're not actually updating the discriminator weights. We're only updating the generator weights. And so in PyTorch, there's a way of turning off the autograd for the discriminator when this is happening. Okay, any questions about this?
Yeah.
Yes?
Would you ever cycle like you're doing that for like batches? Oh, sorry, no, it's all right.
That's okay. If you think of a question that you're going to ask a bit later, yeah. Okay, so here's some details about the architecture. So first, we generally we normalize the images between -1 and 1. It's a bit more convenient. So when the images are given to us, often they're originally normalized between 0 and 1, the pixel intensities, but it's because of variance reduction and stuff, it's better to change it so that it's 0 to 1. So -1 is black and 1 is white, or if it's a color image, +1 is the full, +1 in the red channel means the maximum amount of red, and so on. Now, we tend not to use pooling layers when we're doing this. So the discriminator, you could use just exactly the same architecture that we used for ImageNet, those architectures we talked about before, where you had convolutional layers and then max pooling layers and then the more convolutional layers. But it turns out for this purpose, it's a little bit better result if you get rid of the pooling layers and just replace them with a kind of fully convolutional architecture. So we did cover this case when we talked about convolutional networks. You just have a stride. You can downsample without max pooling by just having a stride, applying a stride to your original image. So you get what's called a fully convolutional network. So you use strided convolutions for the discriminator, and then for the generator, well, here's an example of what a generator looks like. So it's the reverse of a discriminator. So you remember we looked at those things like LeNet and AlexNet, where we started with convolutional layers and then had fully connected layers. Well, this is kind of the same thing in reverse. We start with, at the beginning is our latent variables, and then we put them through we have the fully connected layers first, and then we have convolutional layers, and the convolutional layers get bigger. Instead of getting smaller, they get bigger until they reach the size of the actual image. And so it's essentially just the reverse of the convolutional network, which is why this is sometimes called a deconvolutional network. And so I guess this is the point. The pooling layers, we can't reverse the pooling. The max pooling loses information. You take four pixels and you take 4 neurons and you just calculate the maximum over those 4 neurons. That process is not reversible. So we sort of want to replace it with something that is reversible. So these strided convolutions are kind of reversible, and the reverse of it is called fractional strided convolutions. So instead of, so it's just kind of, the natural way to reverse this. We talked about batch normalization, so we use that for both the generator and discriminator. Remember this, when you put the generator and the discriminator together, you've got a very deep, when we talk about backpropagation, it's the entire number of layers in the generator plus the discriminator which is relevant, because that's how far we're backpropagating. So you need batch normalization to keep the derivatives healthy. Sometimes we get rid of fully connected layers altogether. These are just kind of details. At the output layer, so for the generator, it's normal to use values in the hidden layers and tan H at the output layer. Remember, -1 is black and +1 is white. For each pixel, we want a value between -1 and 1, so tan H will give us that. And for the discriminator, it turns out that leaky ReLU is the best choice. I'm not sure if I mentioned leaky ReLU, but it's the same. It's very similar to ReLU, but instead of for ReLU, the activation is actually 0 when x is negative. For leaky ReLU, there's a slight slope. So maybe the activation is equal to x when x is positive, and maybe equal to 0.1x or 0.2x when x is negative. So there's a very slight slope in the negative region. But again, all of this just came from people trying different things out and seeing what worked best. Okay, now once you've trained this thing, so let me just go, I should have tried to... I should have tried to get this in here, but I just... this is one of the reasons that GANs... this is sort of one potential explanation for why these GANs do a good job. It's been noticed that deep networks are easily fooled. So this, if you take a network like AlexNet that's been trained on the ImageNet database for classification, we talked about how the number of parameters is very huge. It's got 60 million parameters and only 1 million images. And it turns out if you're given such a network and you have access to it and you know the weights, then you can easily fool such a network. So there's examples where you take a picture of a dog, you take a picture that's correctly classified as a dog, and then you add just a tiny amount of, make very subtle changes to this image which a human won't even notice, but has been carefully crafted with the knowledge of what the network weights are, and you get an image that looks identical to us, but then the network is very confident that it's an ostrich instead of a dog. The face does look a little bit like the face of an ostrich, but yeah, it's they look the same to us, and so well, this is an experiment that was done in Jeff Clune's lab in 2015 with. These guys took that. They took that pick breeder system. So remember the pick breeder system where you could breed a snowman or a butterfly. So instead of getting a human to do the choices, they fed the images into ImageNet. So the system produces 15 items. Let's suppose you want to have an image that looks like a strawberry. Right? So you generate 15 random images. Instead of showing them to a human, you feed each of those images into ImageNet, and strawberry is one of the categories in ImageNet. So you pick the image from those 15, you pick the image that is classified most strongly as a strawberry, and then you repeat the process. So this is like evolution. This is artist-critic coevolution, but the critic is not changing, only the artist is changing, the critic is fixed. And the results are very interesting because you see, so this is a strawberry, or it does kind of look a little bit like a strawberry, but these are all very stylized. That's a ski mask, four-poster bed, a soccer ball, the computer keyboard. Well, some of these things don't really look like what they're supposed to, but might have some features. So you see what's happening is that if the network has the network has these weaknesses that can be exploited. We know that the network, it's possible that it's fed an image that not really an ostrich, but it thinks it's an ostrich. And so the genetic program is learning to exploit weaknesses in the network. Yeah. Now, but the network is not changing. The discriminator is not changing, so its weaknesses are preserved, and the generator can exploit them. Now, what happens in the GAN situation is that at one point in time, the discriminator may have a weakness that it can be fooled into thinking that a dog is an ostrich, but then the generator will try to exploit that weakness, but then the discriminator is further trained and it may learn to get rid of that weakness. It may learn to correct that error that it's been making. So you do get a benefit from this kind of coevolutionary dynamics or adversarial dynamics. Now, what can you do with GANs? I'll say a bit more about this later, but this is one thing that you can do with GANs. You can you can kind of do. We could do this with autoencoders as well, but also GANs. The kind of vector arithmetic that we talked about with language, you could try to do that with images. So if you remember with language, we said that king plus queen, king minus man plus woman equals queen, or something like this. We were able to get out these linguistic relationships. So here, if you've got a huge number of images in the beginning and some of them are of smiling women, you can kind of take an average over those images and get a kind of generic smiling woman, and then you can take a woman who's not smiling and you can add a man who's not smiling and maybe you'll get a man who's smiling. So you get this kind of arithmetic, and then or another example is adding glasses. I mean, this is you could perhaps do this just with Photoshop or something, but it's another example. Man with glasses, man without glasses, woman without glasses. You get a woman with glasses. But here you're actually, there's something a bit deeper going on. You're preserving the masculine features, but adding the smile. Although this work has been improved upon since then. Yeah, some of these images do look a bit sort of creepy, actually. Now, so these GANs are they produce very realistic images, but you get certain other problems emerging, and there's the literature on coevolution would. If you're familiar with the literature on coevolution, you wouldn't be surprised about this. They can oscillate, they get stuck in mediocre stable states. So the system can kind of break down. So the two main ways it can break down is the following. So one is called let's take in the opposite order. So mode collapse means, remember in this original GAN architecture, the generator is only rewarded for producing a realistic image. It's not required to produce the full variety of images. So you could have a situation where it's producing very realistic looking images, but they're all very similar and only cover a very narrow range of the original images. Maybe the original images cover many different types of animals, but actually the generator only produces images of dogs, but the discriminator is still happy. So that's called mode collapse. Or in an extreme case, maybe it'll just produce one image with a few minor variations. The other thing that can happen is oscillation. So this is where the thing trains for a long time and it produces a variety of images, but the quality isn't that good, and you get a kind of, let's say the image, I don't know, let's say the images include both bedrooms and kitchens. The generator could go through a phase where the kitchen images are good but the bedroom images are bad, and then the discriminator focuses, as a result of a discriminator focuses its attention on the kitchen images and not the bedroom images, and then it switches the other way and the generator improves the quality of the bedroom images but the kitchen images deteriorate. And it can sometimes go kind of back and forth this way without any actual improvement. And okay, so those two things. And there's special things that are, there are certain techniques people have come up with for trying to avoid mode collapse. So there's conditioning, or I just mentioned them here, conditioning augmentation, mini batch features, which is similar to fitness sharing in evolutionary computation, and like unrolled GANs. So there's various different tweaks to the original algorithm, and there's so many tweaks that some people have referred to this as the GAN zoo. The GAN zoo, because there's like the A GAN and the B GAN and the C GAN and the D GAN. All these modifications of the GAN with different letters stuck in front. This is just one small subset of variations on the GAN. Context encoder, image in painting, conditional GAN, stack GAN, style GAN, and so on. Yeah, so it's a big kind of area. It's a bit hard to keep track of all of these things. Okay, I think we'll take our we'll take our break a little bit early today. We'll have a 10-minute break now, and then when we come back, I'll just kind of go through a bit of a review of the whole course and say a little bit about my own interests and a little bit about the exam. Yeah. Weight sharing? Yeah. Yeah. Uh-huh.
Adding a unit after a unit. Will it make any sense?
A unit after a unit. I'm not sure. What do you mean by that?
I'm trying to re-extract features from training yourself first unit.
Yeah.
And then going through the whole unit structure again to get the final units.
It's like a Siamese. You apply one unit and then you apply another unit.
Yeah. I try that. Didn't quite improve much, but I don't know if it is my tuning problem or is it just use this from the structure that
What task are you trying to do?
Project for live multiple.
Oh, yeah.
And I'm
The
trying
computer vision.
yeah, and I'm trying to like like detect the vessels.
Oh, yeah. In the eye.
Yeah.
Oh, yeah, that looks interesting. Yeah.
And this is the bronchures.
Yeah.
Lung cells. And then it's after first handling, it's just
Oh, right.
lost
Uh-huh.
details. Thinking if I can extract from this image and try to use the bronchial again to improve evidence. Transfer learning I'm actually doing right now. It's not working as well. It's just kind of stuck there.
Yeah, it's a bit beyond my expertise. I know people have tried to use GANs to do this task, but the UNet. So you're using a UNet now?
Yeah, I'm using
Yeah, I'm really not sure. Yeah, I mean, it seems like a difficult task. Yeah,
you get really high accuracy on it, but similarities are another thing.
right.
Because you have a large area of black backgrounds.
Right.
But so accuracy should be high. If you're just putting a black image.
Ah, just the L2.
I
Yeah.
mean, is there any tuning for a network to improve similarity rather than accuracy, like any loss function? Should have done loss function.
Really not sure. I mean, I know people have sometimes added a discriminator on top of this kind of architecture to get get some sort of GAN-like behavior, but whether that would do anything good in this case, I'm not sure.
It's a little bit complicated.
Yeah.
Thinking of an easier way to I actually tried to use several layers of several layers of to the combinational layers.
Yeah.
With just one with just the kernel size of one.
Yeah.
Trying to like finding a combination before the last output layer, to find a combination of this layer outputs which might produce a better output. I think like do something like.
This is the computer vision course. Do you have a tutor or anything?
Yeah, I have a tutor, but
Who's your tutor?
it doesn't quite
Oh,
show
yeah.
up a lot.
Sorry?
It doesn't quite show up a lot.
Oh, what's the name of your tutor?
That's another good question.
What does he look like?
How can I describe it? It's kind of hard to describe.
I don't know, because I know there's a couple of graduate students in Somya's group who know quite a bit about UNets. One of the, I mean, they may be really able to give you some help.
That's right.
One of them's called Gihan.
Yeah, the presentation is tomorrow actually. I'm just
Oh,
desperate
yeah.
to try to get it.
Oh, the demonstration's tomorrow, is it? Yeah.
I tried all weekend to
Yeah.
because something like this, because I kind of always produce a curve like this.
Yeah.
It looks good. It don't go off.
That's the L2.
It doesn't go off. I don't know how to
This
do
is
it.
the L2 distance between the images, or what is
It's
this?
the accuracy
Of what?
of the
Classification.
actually classification.
Right.
It's actually I'm using softmax
Uh-huh.
and the cross entropy for the loss function.
Right.
Yeah, Yeah, but the thing is, it just.
Why is
doesn't
the
go-
accuracy higher for the test set? Is that right?
No, I'm not quite sure. I looked it up online. It
Yeah.
says kind of thing because I use dropout layer and keyword will just
Possible.
perform this way, something like
Did
that.
you do cross validation?
I think it's cross validation. I'm not quite sure what keyword does for validation because it just lets you. It just lets you input a parameter for station.
I mean, it's hard for me to say whether that's a good result or a bad result. I mean, can you compare it to what's been previously published? Or hard to say.
I don't know. I'm just trying to. I mean, when let's say when accuracy just doesn't improve
Right.
anyway, you tune it,
Yeah.
you tune around it. This suggests me to like change the network structure. How to change the network structure to make it more complex or less complex? Because there's no way to tell. It's
Yeah, I
overfitting.
don't really have a good intuition about these units. Did you try to do transfer learning? Or
Yeah, I
what was the
tried.
auxiliary task?
I tried the transfer learning. It wasn't quite good
Yeah.
actually. It kind of converged fast.
But what was the other task?
Pardon?
What was the task that you used to transfer?
Oh, another unit.
No, but was trained on what?
Training on the output. Training on actually. Training on the last
Oh, yeah.
layer. No, not quite the last layer.
Mhm.
This layer.
Oh, yes,
This
okay.
layer output from the first unit.
Oh, I get it, yeah.
Yeah, and this layer kind of produced something that's not. This layer kind of produced something more. I put all the layer
I
out.
just, I'm a bit out of my depth here, I guess.
Yeah,
But,
after something like this, I
Yeah,
thought
yeah.
I can kind of like find
Yeah.
a way to combine them together to get the final output. So I tried to use, like I said, several conditional layers with just one kernel of size one.
Right.
Yeah, try to find a way, and they converge fast. Just don't improve and.
Yeah, I don't know, it's a bit beyond me.
How would you tune networks?
I'm not sure. I mean, how long does it take to run the thing?
Quite slow, actually. It's always 10 approaches.
I don't know. Maybe we can talk a bit more at
Yeah,
the
of
end.
course.
Let's come on at the end. We can talk more of a chat.
Peter, I just wanted to I wasn't very clear on the deconvolution part. I didn't really understand that. The deconvolution.
Oh yes.
So, what exactly is that? Can you just tell me how does that? I don't really understand how it becomes bigger.
Well, you have a filter that kind of.
And it is mentioned as fractional stride. So
Like
fractional.
let's say for every
What is?
pixel you turn. For every pixel in this layer, you create 4 pixels in this layer. Let's say. But each one has its own weights. So you have
Okay, one pixel to pixel, new pixel 1 has one weight, pixel to new pixel 2 has another weight.
That's
so
right.
4 weights.
exactly.
That
And
is
then you
deconvolution.
double the size of the image when you apply that. You double it in both directions.
Yeah, that makes sense. And in this picture, so does this mean there are 9 input images here, and is that how these 9 images are generated, or is it like across one, like 3 into 3? How
I
is this?
think they get a vector and then they just add a bit of noise, like take slightly
Yeah,
vectors just slightly around that vector to
so-
get these different images.
So this requires a 9 vector 9 images here, 9 images here, and 9 images here, is it? And you just add them up and you get this.
I think so, yeah. Or you just have one set of latent variables and then you take small changes in the latent variables, make small changes in the image.
Okay, you are basing it only on these 3 images.
That's right. Gives you one vector and then you're just adding a little bit of noise to that vector.
And it's generation, like whenever all the GAN examples are like generating images, like what can you actually do? I mean,
It's a good question. Look, I'll get to that in a bit. I'll get to that at the end. Yeah. Good. So this these are the topics that we planned to cover, and I think we did actually cover them all in the right order. I wasn't sure at the beginning whether we would need the week 11 lecture, but with hard work and concentration, we've fortunately managed to cover all the material in one less week. So this is good because it'll give you a bigger gap between the last lecture and the exam, so you'll have some more time to absorb the material. And as you remember, this is the assessment for the course, 16% for assignment 1, 24% for assignment 2, and then the written exam. Now, I'm just briefly going to kind of go through all the topics just to kind of give you a feel of the overarching view of the course, right? So we started out, first we talked a little bit about neuroscience and the structure of the brain and so on. That stuff was mainly just background. But then the first technical topic was this McCulloch and Pitts model of a neuron, which was used to make the perceptron. And then we had the perceptron learning algorithm from Rosenblatt, so how to update the weights to learn a linearly separable function. And we talked about the limitations of the perceptron, so it can learn, if it's linearly separable, it's guaranteed to learn the data, but there are some quite simple functions that are not linearly separable. And we discussed how you could, by hand, build a multi-layer network to compute a given logical function. So if I give you the logical expression, you can construct the network, but then we wanted to have a way to learn the network weights from the data, right? So this moves on to backpropagation. So first we discussed about different types of learning. So this, and the course was very sort of nicely broken up into these different parts. So we first talked about supervised learning and then reinforcement learning and then unsupervised learning. And with supervised learning, we talked about, right, so supervised learning, the agent is presented with examples of inputs and the target outputs. And you have a training and a test set, and you try to avoid overfitting. And we talked about overfitting and generalization and Occam's razor. So you want to have a compromise between the complexity of the model and how well it fits the data. And we looked at these traditional two-layer neural networks with a hidden layer. And we talked about how training the weights of a neural network is like local search in weight space. And that original activation function, because it had creates sort of flat regions in this space where the thing can get stuck and not progress. And so in order to smoothly move down to find a lower value, we have to have an overall function that's smooth and differentiable, so we can achieve that by changing the activation function to be smooth. So we got rid of that step function and replaced it with either the sigmoid or tan h, and then we talked about how to apply the chain rule and compute the derivatives and train the network, right? So we have an error function. So the first function we discussed was the sum of the squares of the differences between the target and actual values. And then you differentiate the error function by the chain rule and so on. You differentiate it, calculate the partial derivative with respect to each weight, and you have a learning rate, and then once you calculate those derivatives, from each weight you subtract the learning rate times the derivative with respect to that weight. So we looked at the details of this, and then we discussed some variations on backprop. We looked at cross entropy, weight decay, and momentum. So to do this, we had to revise a little bit about probabilities. So the cross entropy, we replaced the square of z minus t with this expression here, t log z minus 1 minus t log 1 minus z. And then we discussed how that can be derived from Bayes' rule and Bayesian inference. And then we looked at weight decay, where we can add an extra term to the loss function which encourages the weights to remain small. And finally, we looked at momentum, where we keep a running average of the differential, and we just kind of update our running average. At each step, we update our running average, and then we use the running average to update the weights. So those were the variations. And we also looked at dropout, which was a way of regularizing these networks. So with dropout, you randomly choose some hidden weights to be inactive, hidden units to be inactive with some probability, and then at the end, all of them are active, but the activation is multiplied by the same probability. And sometimes the inputs can also drop out, but not always. Then we looked at how to analyze the hidden unit dynamics. So we looked at these kind of hidden unit diagrams for the encoder task. We looked at Hinton diagrams for these larger tasks like autonomous driving. And then we were discussing the limitations of two-layer networks and ways of building deeper networks. So we talked about how we could devise function, you could generate data which actually can't really be learned by a two-layer network, but can be learned by a three-layer network. And the problem of vanishing and exploding gradients as the network becomes deep. And we looked at a number of ways of dealing with these vanishing and exploding gradients. So one was to replace the activation function. So this is the rectified linear unit that was mostly used throughout the course, and also the sigmoid and the hyperbolic tangent. We looked at weight initialization, where you choose the initial weights from a Gaussian distribution, but you choose the standard deviations very carefully based on the number of the number of neurons in the previous layer and the next layer. And we also looked at batch normalization, where you compute for each hidden node, you compute the mean and standard deviation for the activations that are coming into that node, and then you make a linear transformation to shift to the mean and standard deviation that you want, and the new mean and standard deviation are extra parameters that are learned by backprop. Then we looked at convolutional networks. So we looked at the general architecture of a convolutional network. It's convolution layers and pooling layers, which gradually get smaller and smaller, and then you have the fully connected layers. We went through the details of how these convolutional networks operate and how you can figure out how many weights and so on are in a network, different strides and so on. We looked at some images of what convolutional filters look like. And then we sort of went through this image process, this ImageNet classification task, and how you can build deeper and deeper networks. And so we were looking at AlexNet, and then residual networks, and then dense networks. Then we moved on to recurrent networks. So we looked at this sliding window approach with NetTalk, and how it was limited because you could only see 3 characters on each side. Then we were looking at the simple recurrent networks, where the hidden units get copied to the context from the previous time, so get copied to the context units. And how we talked about how that can be trained by backpropagation through time. So you unroll the network, and it becomes equivalent to training if you know the depth, it becomes equivalent to training a feed-forward network, but with weight sharing. And we had a little bit of a look at how this can be trained on simple language tasks and what goes on in the hidden units. But then we discussed about long-range dependencies. So these simple recurrent networks could learn like short-range dependencies, but not long-range. And so then we looked at these other architectures that are better at handling long-range dependencies. So long short-term memory and gated recurrent unit. Then we moved on to language processing. So we looked at how you can construct a co-occurrence matrix from a text and how you can use it to make word embeddings. We were looking at singular value decomposition, and you can use the first, choose the first few rows of the unitary matrix to get meaningful word vectors. But we talked about how this is too computationally expensive, and so we need an approximation. And the main one that we focused on was this word2vec. So we talked about this. So you feed in the context word. Well, there were 2 ways of operating it. Either you feed in the surrounding words and you try to predict the middle word, or you do it the other way around. You feed in the middle word and try to predict the context words. And this was a linear model, and then we discussed about efficiency. It's expensive to use softmax because you've got to compute the probability for every word in the dictionary. So we can save time by using hierarchical softmax, putting things in a Huffman tree, so every output is just like corresponding to a node in the tree, and you only have to compute the nodes that you follow to get down the tree. And we also looked at negative sampling, so instead of calculating a probability for everything, we just pick some at random, and we try to reduce the activation for those random ones that we picked and increase it for the correct word. And we looked at, once these word embeddings are obtained, we looked at how they can be analysed and used for certain purposes, so we can get this kind of word vector arithmetic where we got out the capital cities and other information. Then we looked at how these vectors can be fed into an actual LSTM for real language processing tasks, right? So you can have a bidirectional recurrent network, and then if you're doing a sequence-to-sequence language translation, the performance was improved by adding an attention mechanism. And with the second assignment, of course, you're looking at some models that are quite similar to this, but it's for It's not for sequence to sequence, it's for classification. So then we moved on to reinforcement learning. So we looked at this framework, this theoretical framework for reinforcement learning with states and actions and transition function and the reward and the policy. We looked at different models of optimality as a fast nickel worth a slow dime. And we looked at various different reinforcement learning approaches. So we had the value function learning, which was TD learning and Q learning. We had the policy learning, which we mainly focused on the policy gradients, although I did also mention the hill climbing and the evolutionary strategies briefly. And then the actor-critic approach, which combines value and policy learning. We talked about the exploration-exploitation trade-off. You have to, in order to learn the thing successfully, you have to sometimes choose a random action. And then these were the different models. So that was the temporal difference learning, where you just have a value for the state, and you need to, in order to make use of this, you have to have the world model. You have to know what state you're going to go into when you do a certain action. And then we had the Q learning. With the Q learning, you don't need to know the world model because it gives you a value based on a state and an action. And even if you don't know the world model, you can still make a sensible choice of action because you just choose the action that maximizes the Q value for the state that you're currently in. And then we looked at policy gradients, where you try to maximize the you try to maximize the probability of, if you get a positive reward, you try to increase the probability of every action that you took, and vice versa. If you get a negative reward, you try to decrease it. And this was the plain version of this algorithm was this reinforce algorithm. So you have the total reward at the end, and you can subtract off a baseline to get variance reduction. And then this just, whether this is positive or negative, determines whether you're trying to increase or decrease the probability of the actions. And we talked about how this could be learned to use Pong from raw image pixels. So that was week 7, I think, and then week 8 we moved on to deep reinforcement learning. So we talked about this Atari situation where you're given a few images and you have a convolutional network, and then you have 18 possible outputs. So we were looking at deep Q learning and how it could be improved with experience replay. So you had one system playing the game and generating experiences that were going into a database, and then a separate thread, a separate process was taking experiences out of the database and using it to update the Q values. Then we talked about this this kind of confirmation bias with the Q learning. The Q is being used for 2 different purposes, and how you can deal with that by having 2 different Q functions. And sometimes it's just one of them is an older and aggregated version, and the other one is more local and up to date. And then we got to this advantage actor critic, which was a combination of the deep Q learning and the policy gradients. Yeah. So simultaneously, you have an action network which is learning by policy gradients, and then you have a value network which is learning by TD learning, and you're estimating the Q value by taking an n-step look ahead. So this was like a method that brought these other 3 methods all together. So that was the reinforcement learning. So then we moved on to the unsupervised learning. So we looked at the hop field network. So this was used for storing and retrieving images or other items. So we have an energy function, and when the things are updated, you calculate the change in energy and then only update it if the energy is going to be decreased. And then we moved on to the Boltzmann machine. So this one was, x's was zeros, plus ones and minus ones. Here you have energy function looks the same, but the values are either 0 or 1. And we want to use this to generate new states rather than just retrieving stored states. And we kind of looked into this a little bit in the mathematics of this and saw how this sigmoid function naturally emerges from the mathematics. So you pick a neuron, and its next value is either 0 or 1 based on the sigmoid of this weighted sum of all the things coming into it. Then the fully connected Boltzmann machine. Some people were asking about this at the break or afterwards. So there's kind of two things going on here. So the first one is that we add the hidden variables, so we get a more powerful Boltzmann machine if we add the hidden variables. So then we can have an energy function over the hidden variables as well as the input variables. And again, these things are all kind of connected. We're all trying to do the same kind of job in different ways, that these hidden variables play the same kind of role as the latent variables in an autoencoder or a GAN kind of thing. They're like continuous variables that, in this case they're not continuous, they're discrete, they're either 0 or 1, but each of them is meant to sort of represent some abstract feature that can be either present or absent in the image. And so adding these and then having a quadratic function on the combination effectively produces a bigger variety of energy functions on the original variables. So we add the hidden variables, but then if everything's connected to everything, it just takes too long to train and converge. So we can make it much faster without losing too much power by just getting rid of the input to input and hidden to hidden connections and only having input to hidden connections. So we talk, because of this restriction in the connectivity, we can train by going back and forth. We fix the inputs and recompute the hidden, and then fix the hidden and recompute the inputs. And so this led to this idea of alternate Gibbs sampling. And someone figured out that if you just do this once instead of doing it multiple times, you get a pretty good result, even though it's mathematically, mathematically it's kind of not theoretically provable that the thing will converge to something sensible, but in practice it usually does. Okay, so that was the Boltzmann machines. Then we were looking at autoencoders. So here, the latent variables are obtained by, you train the output to be the same as the input, and then these latent variables emerge in the middle as a result of the training. They're continuous latent variables. We talked about how there's a risk of just having a kind of trivial mapping, so there's different types of regularization that can be used to avoid that. And then we talk about this in the context of different types of generative models. So the Boltzmann machine, the autoencoder, and the GAN are all different kinds of generative models. They're all models which aim to produce new items or new images from latent variables, and technically the variational autoencoder generative models can be just divided into implicit and explicit. So the variational autoencoder is classified as an explicit model because you can write down explicitly what the probability distribution is that the images are generated from. And you can also, given an image, you have a backward map from the image back to the latent variables. GANs are classified as an implicit model because you only have a map in one direction. You don't have a map going from the image back to the latent variables. You only have it forward, and so there's no kind of explicit probability distribution written down, but somehow this network generates these images which come from an implicit distribution, and then you rely on the discriminator to make those images realistic. So just, recap on the variational autoencoder. It relied on having a Gaussian distribution and the KL divergence. So it's a kind of an autoencoder, but at the hidden units you produce, for each hidden unit you produce a mean and a standard deviation, and so you take the mean and add a bit of noise based on the standard deviation, and that's what gets fed to the decoder, and you have this extra term in the loss function, which is the KL divergence between that little distribution determined by the mu and sigma and the standard normal distribution with 0 and 1. And then we looked at some examples of the variational autoencoder, and we saw that it does digits pretty well, and faces, but the result is a bit fuzzy, so that's what's kind of led us on to the generative adversarial networks, which we just spoke about an hour ago. So here you have a generator, and then you have a discriminator, and the original model was zero sum, but then we'll kind of replace this to something that's not quite zero sum, but still adversarial, and the details of how to train it, and then the more realistic images. Okay. Good. So that's kind of the whole course in 20 minutes, but everything gone through very quickly. But the idea is to try to see the whole picture and the connections between the different models. Okay, now so let's talk a little bit about the exam. Now, the exam, because of the size of the class and the logistics of the thing and the time frame, we have to go with a multiple choice exam. The questions will be similar to the quizzes and the exercises, but will be phrased as multiple choice questions. So you'll have a question, and then you'll have 4 options, and you have to choose the one best answer. So some courses have exams where there's multiple correct answers here, and there's marks taken off for incorrect answers. So in this course, you just choose the best answer, and there's no marks off for wrong answers. Right, so just for each question, try to find the best answer you can. We try to cover all aspects of the course in roughly equal proportion, and it's divided, so there'll be some questions which are worth 1 mark and some which are worth 2 marks. Roughly speaking, the 1 mark questions are in the similar style to the quiz questions, and the 2 mark questions are in a sort of similar style to the exercises. So I've think I've updated all of this here. If you go to the web page, here's the quizzes. All the quizzes are up there, and there's sample answers for all of them, and the same with the exercises. So go and have a look at them. And so the reason we have 1 and 2 mark questions is because some questions will take you a bit longer to do than others. So we think it's better to have the division there. And we've tried to structure the exam so that the shorter questions are at the beginning and the longer ones at the end. We've tried to do it as best we can. And the total number of questions is not excessive. It's a 2-hour exam. You should be able to answer 32 questions within 2 hours. That's nearly 4 minutes a question, I guess. Yeah. So this is just a very quick. I mean, this gives you an idea. This is just meant to give you an idea of how these 2 examples are just taken directly from quiz and acute questions, but it just gives you an idea of how the conversion can happen. You just ask a question and there's 4 options, and the same thing with the exercises. So the best preparation is to work through the quizzes and the exercises. So there'll be a similar style. Some of them may be almost identical content to the quiz and tutorial exercises, or with slightly different numbers. Some of them might be a little bit different. So primarily you look at the quizzes, but also go back to the lecture slides and try to understand the material in the lecture slides, because there may be questions which are similar in style, but cover slightly different aspects of the lecture slides. Okay. Now, any questions about this at this stage? Now, I just wanted to, we will end a little bit early today, but I just wanted to talk a little bit about my own research, because some of you might be interested in what kind of things I'm particularly interested in at the moment in this area. So one of the things I've been working on is computer-generated art, and this is using that kind of coevolutionary framework where you have a genetic program producing images and then a neural network critic. And if you go and have a look at this website, you'll see a lot more information about this this work. I just wanted to show you a little bit about this. These slides are on that website. Yeah, so this is just a little bit more detail about what we were already talking about. Yeah, so we talked about this artist critic coevolution. It was actually Marcel Duchamp who really emphasized this, the role of the spectator in the creative process. Now, we went through most of this here. Now, I just mentioned, so one way of GANs have been used to generate art. So one way of generating art is using GANs. And this is some examples of GAN-generated art. These top 3 examples are from Robbie Barrett. So what happened, I don't know how many of you know this history, but like these Goodfellow and so on, these guys came up with this GAN algorithm, and then an undergraduate at Stanford University kind of implemented it and put his code on GitHub. And so in this case, the network is trained on actually human art. So you feed in a bunch of artworks by humans, and then you ask the network to try to produce another artwork in a similar style. And this last image, these 3 French guys kind of forked Robbie Barrett's code, and they trained a system on a bunch of portraits, and they created this image and sold it at Sotheby's, and it went for some huge price that no one was expecting. I don't know, $400,000 or something, and it's pretty ugly actually. Well, it depends on your sort of taste, but it's sort of this little inscription down here is actually the Gann equation. It says min of max of something, something, something. So that's actually the Gann equation in the corner. And it's a fake portrait, but it's said to be a portrait of someone, Monsieur le Bel-Ami, you know, the name Bel-Ami. And Bel-Ami is actually the French translation of the name Goodfellow, right? So there's these sort of hidden jokes in there. But if you want to create art in the style of humans, another way to do it is the neural style transfer, which we talked about. So this process takes longer, but you have more control. You can pick exactly the content you want and exactly the style you want, and you know, create artworks that way. Okay, I think we discussed this. So that's one of my interests. And but I guess like my interest is more not creating art in the style of a human, but maybe like some other style that the computer may come up with its own style. It's not trained on artworks. It's just trained on photographs, and the idea is it's trying to make an image which is of low algorithmic complexity, but is good enough to fool the critic. So it's a way of generating kind of abstract art. Now, another thing that I'm interested in, someone at the break was asking, well, what are GANs used for? That's actually kind of a good question. I'm glad you asked that. So GANs, some people are using GANs for design, as an aid in design. You know, let's say you want to design new handbags. There are systems where you can train a GAN on a bunch of existing handbags and then ask it to kind of produce images of new handbags, or that's just one example, or shoes, and it may prompt you to think about new design options that you hadn't previously thought of. That's one purpose. Another purpose is sometimes used in supervised learning for generating auxiliary data. Like you have a supervised learning task, you have medical images and people have a certain disease, but you've only got a small number of images where people have the disease and a larger number where they don't have the disease. You may try to use a GAN to generate fake data of what the images might look like for people who have, you know, similar to the ones of the people who have that disease, and then that may actually improve your classification. So that's another purpose. But what I'm more interested in is a set of tasks which are known as attribute swapping. So this is most easily understood in terms of facial expressions. When I searched for this last week, I had trouble finding good images, but I managed to find this one today. I think it's a very recent one. So the idea here is the top image is, you feed the system the top image and the bottom image, and it produces the middle image. So the idea is it's trying to preserve the identity of the top image, but the facial expression of the bottom image, right? So you take this person but give them that expression and it turns into this. And so this, you know, we can call this face swapping or expression swapping, but this, it could be thought more generally in terms of attribute swapping. So even the the neural style transfer can be done, can fit into this paradigm too, because the identity, instead of preserving the identity of the person, maybe you're preserving the content of the image. You're splitting it up as the content of the image and the style of the artist. Here it's being split up as the identity of the person and the facial expression. So there's a number of different ways to do this, and for faces, if we're talking specifically about faces, the most impressive work actually is very specific to faces. They have have a 3D model of the person's face and all this kind of stuff, and this is what people are using to make these deep fakes. But some other ways to approach the same problem, you can use autoencoders to do this. So let's say you put in you have a database of celebrities, and you have the identity of each, there's 200 different people, and for each person you have multiple photographs with different facial expressions, but you know the identity of the person in each photograph. So you train an autoencoder, but you split the hidden nodes into two groups, and one set of hidden units you also use to train a classifier. So the classifier is only going through these units and not those units. And the idea here is that the information relating to the identity of the person should then concentrate itself in these units, and then those units will learn the facial expression, let's say. So once this is trained, then you can take two different images. You say, I want the identity of this person, so you feed that into these hidden units, and the facial expression of this person, you feed that into that, and you get this combination. So this kind of architecture can be used to do this task. It doesn't produce quite as good a result as this, but it produces a reasonable result, and then there are other ways to modify this architecture to get improvements. And there's another model that I've got interested in lately, which is called a bi-GAN. What happens here is, this is kind of a mix between a GAN and an autoencoder. So the GAN, you have a generator and discriminator. With the autoencoder, you have a generator and an encoder. There are a number of models that have been proposed where you have a generator, an encoder, and a discriminator. And people are still kind of figuring out the best way to achieve this, but the idea here is you try to get the benefits of the autoencoder and the GAN. So the GAN produces good images, but the GAN doesn't normally have this reverse map. If I give you an image, you can't tell me what the latent variables are. So this model tries to do everything. You can convert the image into latent variables, you can convert the latent variables into an image, and the discriminator here accepts not just the image but also the latent variables. So it's given a pair ZX, and it's trying to distinguish, okay, did this pair emerge from starting with a real image and turning it into a Z, or did it emerge from starting with a random Z and turning it into a fake X? Yeah. So that's a related thing, but all of these all kind of fall into this area of representation learning. Right? So in theory, these methods can be applied to a lot of different tasks. If we can learn a good mapping from images to latent variables, one of the things people are doing with this is trying to use this as a component in deep reinforcement learning for video games. You have a map from the image to a smaller number of latent variables, and then you try to do your reinforcement learning on these latent variables instead of on the original image. Or another example is visual question answering. Like you take an image and you use YOLO to separate out the objects in the image, and then you identify the object, but you try to get this kind of split happening where you have some units to identify the object, but then you have some residual things which tell you what type of object it is. Yeah, okay, this tells me that it's a motor car, but maybe this gives me some information about what type of motor car. So this is actually a kind of big area people are interested in at the moment, is this kind of representation learning. Okay, any questions about that? So, where are we? Please fill in the UNSW My Experience survey if it's still open, if you haven't filled it in already. And I'll try to, I think the exam is on Saturday week, is that right? Or so I'll try to maybe set aside a 2-hour period or book a room or something where we can have some pre-exam consultation if anyone wants to come and ask questions. I'll try to find a time when that's convenient for everyone, maybe Thursday of next week or something like that. Okay, any final question? Oh, sorry, I should also mention this week we're having those additional, so we have these additional lab consultations happening, they were in weeks 5 and 6, and then they're happening again this week, weeks 9 and 10. I think tomorrow, there's two tomorrow, 2 on Wednesday and 1 on Friday, so come along to those if you need help in terms of the assignment. And does anyone have any final questions? Good. Okay. Well, thank you for your attention, and good luck in the exam. Hey.
Pat, thanks for asking about the assignments.
Yeah.
Just to check what you're saying.
Oh, yes.
For the measure part of the LST and efficiency.
Yeah.
So I get the output, and then that's numbers that are positive, negatives.
Yeah.
And then I read on the front that the tutor said to have it softmax. But I was thinking because softmax puts the entire tensor in the range of 0 and 1. Is that right?
Softmax. Well, it's for it's binary classification, right? So it could be done with softmax with 2 outputs. Which is essentially the same as having a sigmoid.
Yeah, that's what I was thinking, because did you just mean, because I know that for the binary cross entropy you just use sigmoid 1, there's a function that replaces it.
Question, is it for part 2?
Yeah, for part 2, the measure part, where you have to establish the range itself, like to compare it between the label and the output, and you have to organize it as true positives and false negatives, those 4 categories.
Right.
Talking about the measures function?
Yeah.
Can't you use like a step function for that?
Yeah, so that's what because the tutor said something about softmax, but
I didn't use softmax and work
yeah, I
fine.
didn't think that was right either.
And then your error function should have the sigmoid attached already.
Yeah, the error's
There's a
fine.
BC, there's a binary cost
Yeah.
entropy with,
Yeah, so I was just asking because the tutor said something about softmax.
I had to
on
convert it to numpy to do Heaviside, but it worked.
You don't, unless the skeleton code has two outputs built in. I mean, you don't. So calculate the true positives, false positives, and so on. You can do that either way. You can do it with the softmax or with the sigmoid.
Right. It just
So the spec doesn't say to use a softmax, right? Or,
the spec just lets you do whatever you want.
Yeah.
You just need your outputs to be 0 or 1 or something.
Yeah. So I
So
was thinking like
you don't have to use softmax. You can just do it with sigmoid if you prefer.
any method that can get it to 0 is pretty much. That sort of
That's right, but softmax would be equivalent to sigmoid. If you sigmoid with cross entropy,
yeah.
that would be equivalent to softmax.
Yeah.
Sigmoid will give you a value between 0 and 1, right? Not necessarily 0 or 1.
Yeah.
Whereas you want 0 or 1.
So then you'd need, like you said,
Because I
you need a
write a series of
threshold.
if else statements to, if it's this and this.
I thought
Yeah,
about,
you have to check if it's bigger than a half
You
or
should
less
check
than
all
a
the 4
half.
cases.
yeah, I thought about that.
Otherwise, I guess you could do the half.
Because you couldn't really just use soft. Puts it in range, and you have to check it differently if you do it.
If you do softmax,
I also wasn't sure. The main thing.
well,
I
if you
wasn't
do
sure.
softmax and just extract, if it's softmax with two outputs,
Yeah.
you can just extract. Let's say the outputs are 0 and 1. If
Yeah.
you just extract output number 1, that will give you a probability. So then you can do with that exactly the same as what you would have done with the
Oh,
with
okay.
the
Oh, because you're comparing two in this
yeah
stage. Right. Okay, I have to look.
sigmoid thing. Yeah.
Thank you very much.
Oh, you still need help with your unit thing or something.
I had a more different question. Was I'm thinking about doing computer science honours next year.
Yeah,
I'm
yeah.
doing mechatronics, but computer science is kind of what I'm more interested in.
Yeah,
Do you take undergraduate honours students?
Oh, yes, yeah.
Okay.
We could talk about potential projects.
Yeah,
So you're looking for something.
It's a bit early now because
Yeah,
it's
yeah,
not till term 3 next, like this.
Oh,
time.
term 3,
term
right.
3 next year. So I was just curious if you took.
Yeah. Just
I'll send you an email.
send me an email. Sorry, I know I've been a bit bad about answering emails, but if you send me an email, I'll try to. We can arrange a time to talk. So would you be looking for something with a sort of robotic flavour or
I
something?
don't
or it
know
doesn't
really.
matter?
I'm not. I was looking for more pure AI, machine learning, networks kind of things. I'm doing robotics honours anyway.
Right.
So I'm not interested in like a more AI
So you're doing mechatronics.
honours. Yeah.
So you have to do a thesis.
I'm
for
doing
that.
thesis already. Yeah. But then I might do another one in computer science.
Oh right, I
Maybe
see.
because-
That's interesting. Oh, you started that thesis already?
I've started that.
Oh
one
yeah,
already,
what
but
are you
I think
doing?
I have to do that.
Yeah,
because
yeah.
all the engineering is honours.
Yeah.
But I'm doing like kind of like path planning, which is one of the things I'm interested in, like
Right.
RRTs, like yeah. So
Yeah.
doing that, but like this kind of stuff, like the art stuff and that sort of stuff, would be something else I'd be interested in.
Yeah.
Cool, I'll send you an email.
Great.
Thank you.
For the assignment, I know we have like the pre and post processing steps.
Yeah.
Is the whole glove vector thing, does that remove all symbols and
I think so. Because
Trying to do some pre-processing about moving punctuations and stop words. Just make a difference.
okay.
I think the punctuation's probably gone already,
Okay. Yeah, because I printed it out and it
but you can put in stop words if you want.
so yeah, just filtering out
That's
words
right.
you might not want. Okay, cool. And for part 3, is there like a distribution of like how you like the I think you know what I'm trying to ask, but
What accuracy should you be aiming for?
like to get like what marks kind of.
Yeah, I mean,
It's just like a see what everyone gets.
sort of see what everyone gets. Yeah.
Yeah.
Well, I think the part 2 I think should already get how much does the part 2 get? 80,
80, 81,
82 or something.
on a lucky
So-
one I get like 84 or something.
Yeah, so I mean, I think if you can get,
Beat
probably
that
if you
away.
can get 86 or so, you probably get maybe half the marks for part 3, and then
Okay.
for the other half, we just see
Yeah.
how
How well
well.
everyone else
Yeah,
did.
yeah, yeah.
Cool. Awesome. Thank you.
Oh, this unit. Oh, yeah, sorry, yeah, so assignment, yep.
My partner focused on part 2, and he kind of have problem with the